Hi, it's Gary. Welcome to today's video. I want you to imagine it's night time. I want you to imagine you're outside and you're looking up at the night sky. What can you see? Well, chances are you can see the moon. That's quite a large object, isn't it? But you can also see stars, and some of those stars, they may actually be planets that are in our solar system. But what are you actually seeing? Well, the simple answer, you're seeing the past. Let me try and explain this a little bit. Light travels, it travels at the speed of light. Now, this is approximately 300,000 kilometers per second. That's fast, isn't it? Now, for most of us, this is negligible, as what we're seeing, they're all things that are close to us, like me to the camera, that's about maybe 60 centimeters. So what I'm seeing from the camera is virtually instantaneous. But when we look up at the night sky, then we're talking bigger distances. Let's start with the moon, that big round object up there. That's about 380,000 kilometers away. This means the light from the moon takes 1.3 seconds to reach us. So we're seeing the moon as it was 1.3 seconds ago. So we're seeing into the past. Let's go a little bit further and let's look at Mars. Now, because of the orbits of the planets, the time that light takes to reach us from Mars, it can vary between 3 minutes and 20 minutes. So we're seeing Mars as it was between 3 and 20 minutes ago. And this, it introduces challenges when trying to control the rovers on Mars. Think about it, Mars, the only planet in our solar system entirely inhabited by robots. Let's use as an example where Mars is the furthest from us, so it takes 20 minutes for light to travel. Let's also assume that the rover on Mars is able to travel at 1 kilometre per hour. The actual speed is a lot less than this, but we're just trying to make the maths easier. The rover, it sends a message back to Earth. It takes 20 minutes for the message to reach us. In this time, the rover has travelled 330 metres. The rover's controllers, they then decide what action they want to take and they send a message back. This takes another 20 minutes before the rover receives this. In this time, the rover has travelled another 330 metres. So that's a total distance travelled of 660 metres whilst the messages are in transit. Then we also need to add on the time it takes to make the decision, so that distance could even be further. Let's jump out a little bit now. We're going to look at Saturn. Well, Saturn, it's more than 1 billion kilometres away from us, which means we're seeing Saturn as it was over 1 hour ago. Let's jump further. We're going to jump outside of our solar system. At these distances, we measure light in what's called a light year. And this, it's the distance that light can travel in 1 year. Light year seems quite obvious, doesn't it? It works out to be about 9 trillion kilometres. So you can see where talking about a light year is a lot easier than talking about multiples of 9 trillion kilometres. The nearest star that's visible to the naked eye is Alpha Centauri, and that's 4 light years away from us. That means we're seeing Alpha Centauri as it was 4 years ago. We're seeing the past. Another star, and it's been talked about a lot lately, is Betelgeuse. This is 640 light years from Earth. If Betelgeuse were to explode today, we wouldn't know about it for another 640 years. But we can go even further than this. Quasars, these are the very bright and also very distant objects. There's a quasar called 3C273. I know, sexy name, isn't it? That's 2.5 billion light years from Earth. The light we see is from 2.5 billion years ago. And think about it, the Earth, it's only about 4.5 billion years old. So the light we're seeing from that quasar, it started its journey when the Earth was only 2 billion years old. And this, it's actually when the first complex cells started to evolve, and 1 billion years before multicellular life. But how do we know how far these stars are from us? I'm saying 640 light years, but how do we know that? Well, this is calculated using something called the cosmic redshift. As light travels, the wavelength it gets stretched so that the light it's seen as being shifted moved towards the red side of the spectrum. Various common atoms have known emission and absorption lines, things like hydrogen, helium, oxygen, and scientists they're able to measure where these lines occur in the spectrum of light from an object. Then they can use that to calculate the distance that the light has travelled. Using this method and multiple observations over a long period of time, it's possible to determine that the universe is expanding. Galaxies, they're moving away from each other as the space between them increases. A good way to think about this: take a look at a loaf of unbaked raisin bread. The raisins, they're mixed in the dough, and we're going to assume here that the raisins, they're representing the stars, and the dough, that's the space. As the bread rises, the space between the raisins increases. The raisins themselves, well, they're not moving, but the space between them, that's grown larger as the dough has expanded. And it's the same thing happening with the universe, which is constantly expanding, and that's what's pushing or moving the galaxies farther apart. This was a simple question, but it rapidly grew into a complex and mind-expanding research opportunity. I hope you've enjoyed today's video. What are your thoughts on the expansion of space? Are you able to add to this? This was just a very quick introduction. Please drop any comments down below. Please hit the thumbs up button. Every time you like, every time you comment, just helps with the YouTube algorithm. If you haven't already, please subscribe to my channel so that you can get new videos as I release them. I'll talk to you again soon.